Okay, okay. So welcome to this second day for this FAIR-DI workshop. I will give an introduction to data reproducibility session, this morning session. Actually, it will be focused on the theoretical data producibility and also on materials. So the question might be rephrased as follows: what is the reliability of databases generated by computers in material science, how to assess it, and how to improve it? Traditionally, it's possible to distinguish the levels of accuracy given by formalism, which is related to mathematical formulation, and the implementations, numerical. The later one is referred to as verification and precision analysis, while when comparing the different formalism, we will aim at an agreement with experiment, and this is often referred to as a validation of the data and also accuracy of the data. Let me show you an example. Traditionally, also in density functional theory, one has different levels of formalism, different exchange correlation functionals. And John Purdue, a couple of years ago, has introduced the so-called Jacob's ladder of DFT, going from the lowest level, which is local density approximation, which is favoring the speed, to the upper level, which is favoring the accuracy, in which one includes different ingredients in order to compute the total energy, also to optimize the lattice parameters and obtain properties related to the total energy. But of course, this view is not complete. And for example, while this is a well-established Jacob's ladder, one can wonder, in computing the lattice parameter and comparing it with experimental results, well, we should also include phonon effect and zero-point motion. And also now to come back to the numerical assessment of the data accuracy, you see that if we focus on one particular level, like the usage of GGA and the PBE functional, shall we obtain the result from all electron calculation, PAW, norm-conserving pseudopotentials? We perfectly know that there will be a spread of the values, and also the different codes, Vin2K, FHI aims, etc., will give slightly different results. Now, that kind of questions have been addressed already for quite a while, and I would like to give the following figure that is taken from a paper from Le Jager and Cottenier with 70 other authors. It was published in 2016. As a function of the year of publication, the silicon PBE lattice parameter is represented. And while PBE appeared in 96, you see that these different points show some spread, which is called the precision spread. And after some effort, the different authors succeeded to make the dispersion smaller. But still, one also see the accuracy, the difference with respect to the experimental data. What do we mean by experimental data? Actually, it's not true experimental data, because the zero-point effect has been removed and it has been estimated in this figure to be 0.3%. The PBE accuracy, as you can see, by comparing this value and that value, is on the order of 1%. So this is not negligible as well. In practice, how will we address the verification and the validation of data? Well, by comparing with references and or doing cross comparison. This would bring an estimation of the fluctuation of the data, root mean square evaluation. And these studies should be done for large sets. Accuracy will be comparing some data with experimental data, or theoretical data with higher level of accuracy, while precision will be done by comparing with theoretical data with better controlled numerics. And for which properties in material science were such studies done at present? For the atomic structure, lattice parameters, for example, and for the electronic structure. There is still a very large number of properties for which such establishment of precision and accuracy was not yet done at all. In quantum chemistry, the effort started already a long time ago. There are some reference sets that are mostly thermochemicals data for hundreds of molecules, some of which are given here. And at the level of the precision studies that have been done, I simply have singled out one example, appeared in 2017, the elephant in the room of DFT calculations, in which the authors claim microartery precision by a comparison between multi-wavelets, NAO, GTO, and APW basis. The situation in material science is not as advanced. There was one milestone that I have already used one figure, the previous validation, comparison between for the silicon PBE lattice parameter. This paper is a result of a very large effort to quantify numerical precision, the so-called delta factor collaboration with 40 methods, in which the energy of 71 elemental solids for different volumes were compared. And so we will have actually a follow-up today by the first speaker, Stéphane Cottenier. Other milestones were for electronic structure. One knows that there are very well-known shortcomings of DFT for bandgap. The state of the art is GW approximation within many-body perturbation theory. The first realistic calculation based on GW was done actually in 1986. But since then, a lot of approximations have been proposed to the exact, in quote, GW approximation. One can do calculation at the non-self-consistent G0, W0 level, or include partial self-consistency, or include electron-hole interaction. Actually, in 2015, from our next speaker today, Michiel van Zetten and co-workers, there was the proposal of GW100 benchmarking G0, W0 for molecular system. And so we will hear Michiel presenting the follow-up. And then more recently, in 2020, by Tonatiuh Rangel and also co-workers, who include our third speaker, Fabien Bruneval, as well as Michiel, reproducibility in G0, W0 calculations for solids. And you see, again, we are at the level of G0, W0, but we do not even consider the partial self-consistency or further refinement of the theory. Today, we will also hear Tianyu Xu, who will present all electron GW calculations. I have still have a couple of minutes, so I will continue to give the broad panorama of the situation. I would like to mention a couple of other noticeable, not exhaustive, of course, publication in the domain of validation, verification, accuracy, and precision. Some of which are co-authored by people who are registered to the conference. I hope that they are hearing, they will participate to the discussion at the end of this morning. This one is about spin-orbit coupling treatment in DFT and looking at band structures, co-authored by Volker at Concham level. Another work by Andris Goulans and co-worker, including Claudia, microartery precision in density functional theory calculation, published in 2018, comparing different techniques, different implementations of some formalism. There is a work also in 2018. A co-worker of this work is Matthias Scheffler, main group test set for material science and engineering with user-friendly graphical tools. In this work, a hierarchy of functionals have been explored, including GGA, hybrids, RPA, Artifoc MP2. Then there is some work related to the band gap of solids, including setting a database of experimental band gaps for 472 non-magnetic materials and computation from 33 existing functionals and also following improvements. And as a final word, I would like to mention one study in which I'm involved, which is the zero-point normalization of the band gap. In this paper, we studied the zero-point normalization in 30 materials and compare the results with experimental data that are available for 18 materials. It was possible to show that the reliability of experimental data is, well, compared to the theory, is on the order of 25%. And you see that for this set of materials, the comparison between experimental ZPR and first principle ZPR is at that level. This includes first principle 0-point lattice parameter change, which has a bearing on the band gap change that can be up to 0.4% for materials with first row atoms. And I connect now even to a question raised by Claudia after Andriy Sakutayev's talk yesterday, whether the inclusion of zero-point normalization is important or not. You have here for different materials, the first principle gap versus experimental gap comparison, which is 1 here and 4% minus 4% width here. By doing G0, W0 calculation, you get these points. By doing a very elaborate GW self-consistent plus electron hole calculation, here you get a slight overestimation for many materials, but including ZPR, you actually come closer to average exact comparison between experimental and theoretical gaps. There are some materials for which this is not observed, but one can comment, well, this is commented actually in this paper, why is there some problem there? Okay, so I'm finished with my introduction, and I would like now the first speaker, Stéphane Cottenier, to enter in the game.